In today's technology world, everyone talks about the cloud, but does anyone really understand what the cloud is? In this lesson, we'll peer into cloud computing in a way that will make the cloud a little less mysterious. We'll learn that resource sharing, servers, storage, applications, and bandwidth is one of the defining elements of cloud computing. But with such resource sharing comes security concerns. If your data is hosted on shared cloud-based servers, what keeps others in the same cloud from peering in? If the cloud provider loses your data, how do you get your data back? What keeps attackers from pretending to be you and using your data for their own purposes? First of all, contrary to popular impression, cloud computing is not just a fluffy marketing phrase. There really are clear technical definitions of the cloud. The National Institute of Standards and Technology offers a 5-point definition of cloud computing. According to NIST, cloud computing involves on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. The cloud is sort of like a hotel as compared to a house. Imagine a hotel as the cloud where you can register anytime, which would be the on-demand self-service part of the cloud. The hotel is centrally located, with many large thoroughfares running right by it, which would be broad network access of the cloud. Where hotel guests share the same lounge, pool, restaurant, and fitness center, that's resource pooling on the cloud. Even if you normally travel to this hotel with just your family, you can still reserve 500 rooms on any given day for a convention or a wedding. That's rapid elasticity. The hotel bills you by the room, by the day, or for the specific items you order from room service. That's measured service. So cloud computing is really just a multi-tenant approach to building data centers. In previous decades, if you planned on hosting the application equivalent of 500 guests at a wedding, you had to build the data center equivalent of a home with 500 guest rooms. It's just more cost-effective to host intermittently demanded services in a shared resource like the cloud. Make no mistake about it, cloud computing is a money saver for business users. In a previous lesson, we discussed cost-benefit calculations like Beckstrom's law. Recall that profit is the name of the game, and one way to improve profitability is to cut costs. Cloud computing cuts the cost of hosting business applications. That's why so many businesses are migrating their applications to the cloud. Remember also that Beckstrom's law featured 2 other cost items that would be good to minimize. One of these is the cost of IT security. The other is the cost of expected losses due to hacking. There is a trade-off between these last 2 cost items. To cut losses due to hacking, you have to invest more in IT security. Likewise, reducing effort in IT security means a willingness to accept more potential losses from hacking. Decisions. The main cost savings in moving to the cloud is just the cost of hosting the applications themselves. There's plenty of money to save in that direction, so even stingy chief financial officers can get excited about the cloud. But the impact of cloud hosting on IT security is less clear. Will the cost of security go up or down when data moves to the cloud? How risky is cloud hosting really? The Cloud Security Alliance is a nonprofit multi-vendor consortium with a goal of educating computer users on best practices in the cloud. The CSA has published numerous recommendations and articles on how to best secure cloud-based applications. One overarching theme in these recommendations is that in a cloud environment, computing is deperimeterized. That is to say, forget about traditional perimeter defense as the main way to protect data. When your data goes off premises, your local firewall does not have much of a role in securing it. Rather, like a stagecoach with armed escort, your data needs to bring its own protection with it as it travels through potentially hostile environments. Data on the road, or camping out in unknown servers, needs to be ready for whatever may come down the network trail. In general, when data travels beyond the local firewall, it usually needs to be encrypted. Encryption is like the safe the outlaws want to crack in order to get at the assets you have hidden within. Some forms of encryption are stronger than others, so for cloud storage purposes, other things being equal, stronger is better. We also learned earlier that encryption depends very much on the management of secret encryption keys. In symmetric crypto systems, both ends of a transaction need identical secret keys. In asymmetric or public key crypto systems, every public key has a partner private key, and these private keys also must remain secure and secret. So no matter what specific type of encryption is being used, key management is always going to be an issue. In cloud computing, there are three basic options for storing secret keys. One option is to keep them yourself. Another option is to let the cloud provider keep your encryption keys for you. A third option is to check in your encryption keys with a third-party provider who specializes in encryption management. Any of these options carry risks. If you keep your cloud encryption keys locally, if those keys are lost for any reason, all your cloud data may become irretrievable. On the other hand, if the cloud provider holds your encryption keys, that cloud provider has a great deal of leverage over your company's data. What if there is a business dispute, or if you want to change providers? There may be a problem getting back both your keys and your data. Finally, it may be attractive to outsource the key management problem to a third party. But what checks and balances exist to keep an eye on that third party? Who watches the watchman, essentially? As data moves over networks to travel in and out of cloud storage, it's also important to encrypt the data in transit. One technique used to create an encrypted network tunnel is called Virtual Private Network, or VPN. A real private network is one in which you own or lease the physical wire and no one else gets to use it. In a virtual private network, the physical pathway is a shared resource with multiple users on it. But from the edge of your local firewall to the gateway of the cloud service provider, VPN traffic is all encrypted. So your packets are traveling through public pathways, but no one can peer into the data. Sort of like a limo with darkened windows. Setting up VPNs to connect local networks to cloud services providers is a fairly normal procedure. To set up a VPN, or just to access cloud services in general, providing proof of identity and authentication is also generally required. In earlier lessons, we consider a variety of ways to prove identity online. Any of these might apply to cloud services. Name and password logins may be good enough for some purposes. In other cases, stronger authentication measures, such as the use of digital certificates or two-factor authentication with biometrics or smart cards, may be required. One common problem in provisioning identity for cloud services is that many cloud-based applications are really mashups of different cloud services provided by a whole series of subcontractors or component vendors. To set up different login credentials on all of these collaborating services is inefficient and burdensome. For this reason, some companies offer Identity as a Service, IDaaS, providing a single sign-on ability in which users authenticate once and then get access to a whole array of different applications and data stores. This type of single sign-on system is very prevalent in directory services for local area or enterprise networks. Such local directory services can also be extended to cloud storage and applications, creating in effect a virtual cloud-based extension of the local area network. All in all, cloud services are very tempting to businesses looking to save money or to gain access to a wide array of turnkey services. In fact, the cloud is so tempting that before long, a business may have so much data in the cloud that they have no quick and easy way to get all that data back. This can cause serious problems for processes like disaster recovery or legal discovery. In general, backing up data in the cloud is not the main problem. Cloud services providers tend to deploy automated backup systems using different data centers distributed over a wide area. However, if the data needs to be deleted from the cloud, or if it needs to be proven that data has remained strictly confidential, things can get tricky. Again, encryption key management is centrally important to managing cloud data security. If a large amount of data needs to be eliminated from a cloud provider's system, shredding the encryption key will accomplish that result in an instant. The bits will still all be in the cloud, but no one will be able to read them. So, is security better or worse in the cloud? The jury is still very much out on this question. Different security techniques are needed, that's for certain. But the technical building blocks of cloud security are familiar core technologies needed for almost any automated data security system. Such technical controls include encryption, authentication, data backup, and network security. Cloud services extend the physical perimeter almost to the vanishing point, but they do not change anything fundamental about the need to wrap your valuable data with multiple layers of technical and administrative controls. Controls of all types, physical, technical, and administrative, are needed to mitigate risk by reducing vulnerabilities. However, there is no such thing as perfect security. Even very elaborate and expensive security systems have potential weaknesses and undiscovered vulnerabilities. So preventing intrusion is just one phase in information security. Beyond preventing intrusions, it's also important to take notice when intruders have broken through. In the next lesson, we'll be covering intrusion detection systems and related technologies for monitoring of data security.